Assalamu alaikum. Welcome to our last lecture in Principles of Computer Networks. In this lecture, we will discuss network security. We will cover an introduction, cryptography, symmetric key algorithms, public key algorithms, digital signatures, management of public keys, communication security, authentication protocols, email security, and web security. Internet has evolved from a small network shared by a handful of universities and institutes to share information into a global network connecting individuals, companies, banks, and all sorts of institutes, conducting businesses, making bank transfers. This made the companies aware of the importance of securing their connections and their e-assets, as well as the governments aware of their responsibility to protect the privacy of the individuals with information shared with third parties such as hospitals, financial institutions, and insurance companies. Security problems mainly came from individuals who are trying to either get attention or to harm someone or to gain something. For example, a student might have tried to have fun with the snooping on people's emails. A businessman can do this to discover the competitor's strategic market plan. An accountant can do this to embezzle money from the company. A spy can do this to learn about the enemy military or industrial secrets. A terrorist to steal germs warfare secrets. Network security problems can be divided roughly into four intertwined areas: secrecy, authentication, non-repudiation, and integrity control. Secrecy is to keep your information secret from unauthorized individuals. Only authorized individuals can get to see the information. Authentication gets to deal with identifying the users of your information to make sure that they are legal users, authorized users. Non-repudiation has to deal with the inability of persons to deny their actions. Integrity has to do with that you make sure that your information is complete, correct, and consistent. Every layer has to do with security. Physical layer, such as doors, locks, security guards, CCTVs, protecting your wires, protecting your computers. Data link layer has to do with packets on point-to-point line that can be encrypted and decrypted, leaving a computer to the other machine. Network layer has to do with firewalls installed to keep packets in and out, and other security protocols that we are going to discuss. Transport layer has to do with entire connection to be encrypted end-to-end, that's to say from process to process. Application layer deals with issues like authentication and repudiation. Our first technology to inspect is cryptography. We will have an introduction to cryptography, substitution ciphers, transposition ciphers, and one-time ads. Cryptography is a technique of coding data, ensuring only person who is meant to see the information and has the key to break the code can read it. The word is hybrid from two Greek words. Cryptos means hidden and graphen means write. Literally, the word cryptography means hidden writing. But in reality, it is the practice for securing information in transition. Simply, we have plain text or the original message, P, go through a cryptography and encryption method, E using a key K to produce a ciphertext C that equals EK of P. This is a mathematical process. In decryption, the mathematical method D is applied using key K to produce the plain text P that is the actual message. If there is an intruder who has hacked the line between the sender and the receiver, they can only see the encrypted message, and because they don't have the key, they cannot decipher it and get the plain text. There are two types of intruders: passive intruders, who just listens to the line, and active intruder, who actually try to alter the message and then resend it. Encryption is the process of creating ciphertext from plain text. That's to say, EK of plain text equals ciphertext, and decryption is the reverse operation, where DK of ciphertext equals plain text. DK of ciphertext equals DK of EK of plain text. The result should be the plain text. The example here is very simple. As if you have a suitcase and you are protecting it with a key. You can simply change the key, but the method itself remains consistent. From a cryptanalyst point of view, a cryptanalyst is the intruder who is trying to break the cipher. He has three problems. Either he has ciphertext only, that means he has to drive the key to get the plain text, and non-plain text when he has a non-plain text with the ciphertext equivalent to it, and he has to drive the key from that, or he was able to decrypt parts of the plain text, then he has to get the key and to get the rest of the plain text. To achieve security, a cryptographer, the one who conducts cryptography, should be able to make sure that the system is unbreakable, even if some parts of the plain text were actually discovered. The first and the oldest cryptography method is substitution cipher. It was originally discovered or invented by Julius Caesar, so it's called Caesar cipher, where he replaced every letter in the alphabet with the third letter from in the alphabet. That means A goes to D, B goes to E, C goes to F, and so on. A word like attack, plain text, would be DWWDFN in ciphertext. At first, this was a brilliant idea and it worked perfectly until the enemies were able to drive the key. Then a slight generalization for Caesar's cipher. It allowed the cipher to have different key other than 3. So K equals 3 or 4 or 5 as you wish. That means the key became a general method and you can circularly shift the alphabet. The substitution ciphers has evolved where there was a different key where every letter was substituted by a specific letter, like the one we see here. A is replaced by Q, B by W, C by E, and so on. So plain text attack will be QZZQEA in ciphertext. This is a really powerful way of encryption because the key combinations are 26 factorial. That's 4 times 10 power 26. It will take 10 power 13 years, even if it took 1 nanosecond by computer to drive one of the permutations. Transpositioning cipher, on the other hand, reorder the letters instead of substituting them. The substitution ciphers preserve the order but disguise the letters. Transpositioning ciphers, they preserve the letters but reorder them. A transportation cipher, as we shall see, is a cipher keyed with a word or a phrase not containing repeated letters. The purpose of the key is to number the columns, column 1 being the end of the key letter closest to the start of the alphabet, and the rest is numbered increasingly. The plain text is written horizontally in rows. The ciphertext is read by columns, starting with the column with the lowest key. As we can see here, our key is MEGABUCK. A being the first letter of the alphabet is 1, B the second letter is 2, C the third letter is 3, E the fourth letter is 4, G is 5, K is 6, and M being the last letter is 7. The plain text is written in blocks of 6 without spaces. The plain text here reads, please transfer $1 million to my Swiss bank account 622. So without spaces, the plain text is written in blocks of 6. 6 is the length of the key. And then the columns are rearranged as in ascending order. So the ciphertext will be A, F, L, L, S, K, and so on. Constructing an unbreakable cipher is easy. Choose a random bit string as a key, convert plain text into bit string, and compute exclusive OR of these two strings bit by bit. The resulting cipher cannot be broken because every possible plain text is equally probable. The ciphertext gives the cryptanalyst no information at all. As you can see here, we have our original message in binary format, and the first pad XORing them will result in ciphertext. We have the second pad XORing them with the message will give you the plain text. One-time pad is a strong cipher only. The key cannot be memorized, so both sender and receiver must carry it in a written copy, and that's a hazard. And total amount of data can be transmitted limited to the amount of key available. The method is sensitive to lost or incented characters. If an active intruder just omit some of the message or inserted some letters, this will cause the message to be completely ruined. There are two main principles in cryptography: redundancy. All encrypted messages must contain some redundancy. That is to say, information not needed to understand the message. All messages should contain considerable amount of redundancy, so active intruders cannot send random junk and have it interpreted as a valid message. That means you can write the message and encrypt it, then write it again and encrypt the whole blocks, the two blocks, the encrypted message and the plain text, where upon decryption, the receiver will match the cipher text to the plain text and make sure you have sent, he has received the correct message. Freshness. Some measures must be taken to prevent active intruders from playing back old messages. Messages has to be time-stamped so that the receiver is sure this is a new message. There are two types of encryption: symmetric key encryption or secret key encryption, asymmetric key encryption, public key encryption. Symmetric key encryption, also known as shared key or private key or secret key encryption, uses the same key for encryption and decryption. Symmetric ciphers considered less expensive to produce and don't take much computation power to encrypt and decrypt. The drawbacks of the symmetric key algorithms is that if an unauthorized person gets their hands on the key, the shared key, they will be able to decrypt any message and data sent between sender and receiver. The transfer of the shared key is the most weak link in the symmetric key encryption. Asymmetric key encryption, also known as public key cryptography, has two separate keys, one for encryption and one for decryption. The one for encryption is public and shared among all parties to encrypt the message with. Anyone can have the public key and use it. Only the holders of the second key, the private key, can decrypt the message. Asymmetric encryption, considered more expensive to produce, takes more computational power to decrypt, and does not handle well large amounts of data. Examples for symmetric key encryption are DES, Data Encryption Standard, and AES, Advanced Encryption Standard. There are other ciphers. Cryptographic algorithms can be implemented in either hardware for speed or software for flexibility. In the next slide, we will see two boxes, P-box and S-box, that are used for implementing cryptography in hardware. The P-box stands for permutation, used to affect transpositioning in 8-bit input, while the S-box is used to perform substitutions for 3 bits plain text entered and 3 bits ciphertext output. The basic elements can be connected together to produce a powerful device called the product cipher. As you can see here, 8 bits enter the P-box being transpositioned, then 3 bits are transformed to 8 bits, then again 8 bits are transformed to 3 bits in the S-box. The product cipher contains several P-boxes and S-boxes. The first symmetric key algorithm to study is DES, Data Encryption Standard, and it's a symmetric key block cipher published by the National Institute of Standard and Technology. DES implementation is an implementation of Festool cipher. It uses 16 rounds of Festool structure and block size of 64 bits and a 64 bits key. Only there are 8 bits that are not used, so it's actually a 56 bits key, producing a 64-bit ciphered text. The algorithm divides the messages into 64 bits using the 56 bits key, using complex combination of transpositioning and substitution and XORing with other few processes to eventually produce 64 bits of encrypted text. As you can see here, the first process is transposition, encryption, and then transposition, encryption, swap, transposition, and then after 16 rounds, you have ciphertext of 64 bits. Simply, we have 6 alterations, before which there is initial permutation, and after which there is another permutation. The right and the block is divided into right side and left side, each of 32 bits, and these two blocks are switched during the alterations. So R of I minus 1 becomes L of I, and L I minus 1 becomes L of I, becomes R of I. This was not strong enough because of the short key. It was broken, and thus came triple this, where the operation or the process is repeated 3 times. As we can see here, plain text with key 1, encryption round 1, key 2, encryption round 2, key 3, K1 again, encryption round 3, producing ciphertext. And the decryption process is the opposite. As this became less secure, there was a call for a new standard, and it was called Advanced Encryption Standard, and the proposal stated that the algorithm must be symmetric block cipher and the design has to be fully public, and the length of the key has to be 128 or 192 or 265, 56 bits. All has to be supported. Both hardware and software implementations are required because this is fully implemented in software, and the algorithm must be public or licensed for on public terms. In 1997, there was 15 series proposals. In 1998, 5 finalists, one from Demon and Vincent, John Demon and Vincent Ridgeman, that was called Rigendale, and one from Ross Anderson, it's called Spirit, and one from Bruce Shimmer, it was called Twofish, and one from RSA Laboratories called RC6, and one from IBM was called Mars. The final contender was in October 2000 was Rajendell, and in 2001 it became the US government standard published in FIPS 197. Rajendell supports key lengths and block sizes from 128 up to 265 and 56 in steps of 32 bits. It's based on Galileo's field theory, and it uses substitution and permutations, and also uses multiple rounds. The features of the advanced encryption standard are it uses SP network used for mixing and shuffling data in the encryption process. It has key expansion using series of mathematical operations and table lookups to expand the key to create number of round keys. And it has byte data, blocks of AES encryption are processed independently, with each block containing 128, that is 16 bytes. The key length can be supported, can be 128, 192, and 256. The longer the key is, the stronger the protection. If you want to look at the most popular symmetric key algorithms, we have this by IBM with 56 bits key, and it's too weak to be used now. RC4 with 1 to 2048 bits, and you should use it with care because some keys are too weak. RC5 with 128 to 256 bits. It's good, but patent, that means you have to pay to use it. Advanced encryption is standard with 128 to 256. It's the best choice. Sprint with 128 to 265. It's very strong. Triple Death with a key of 186. It's good, but it has its problems. Twofish with key of 128 to 265 bits. It's very strong and widely used. As for public key algorithms, we're going to discuss RSA, Raves, Shamir, and Adleman. These are, as we have said before, key distribution was always the weakest link in the crypto systems, where the secret key should be kept secret because it's the same key for encryption and decryption, and if the intruder finds the key, then there is no meaning for the whole encryption-decryption thing. In 1976, two researchers at Stanford University, Duff and Hellman, proposed a radically new kind of crypto systems. It depends on two keys, one for decryption and one for encryption. They are different keys and they cannot be derived, or it's very hard to derive them from each other. That's to say, decryption of E of P equals P, and it's extremely difficult to deduce D from E. E cannot be broken by chosen plain text attack. These were the requirements. The method works simply as this. A person, Alice, wanting to receive secret message. First, she drives two algorithms, D of A and E of A, meeting the above requirements. Encryption algorithm and key E of A is then being made public, hence the name public key cryptography. In contrast of the traditional secret key cryptography, Alice publishes the algorithm along with her public key, and the private key for decryption, D of Alice, is kept private. How can Alice and Bob establish a secure channel? Simply, both Alice and Bob public keys are supposed to be public. Then Alice will take public key of Bob and take the plain text message, computes EB of P, and send it to Bob. Bob will decrypt it using his private key. That's to say, DB of EB of P equals plain text. No one else can read the message because no one else has Bob's private key. Only Bob can decrypt the message. So public key cryptography requires two keys, one public used for encryption by everyone, and private key only the user of the decryption algorithm has it. As we can see here, Bob sends hi, hello to Alice, encrypted with Alice's public key, and the encrypted message will be sent to Alice. Even if there is an intruder, they won't be able to decrypt it because they don't have the secret key. Alice will use her private or secret key to decrypt the message and get the plain text. RSA, or Raves, Shamir, and Adleman, is a public key algorithm. It has two chosen large prime numbers, P and Q, typically 1024 bits. Then we compute N, which is the product of P times Q, and Z, which is the product of P minus 1 times Q minus 1. Then we chose a number relatively prime to Z, let us call it D, and find E such that E times D equals 1 mod Z. The ciphered message will be P power E in plain text power E mod N. And the ciphertext will be C power D mod N. Knowing that factoring large numbers is very difficult, this is where the strength of RSA comes from. In the example here, we see that P is 3, Q is 11, N equals 33, the product of P times Q, Z equals 20, the product of 2 minus 2 times 10, D equals 7, and E will be 3. We assume that the public keys of Alice and Bob are known, but there is a scenario that we didn't go through. Assume that there is an intruder in the middle of Bob and Alice, where Alice sent a GET request for Bob's homepage to get the public key of Bob, and the intruder, Trudy, was in the middle. Instead of sending her the homepage of Bob, she will send her a fake homepage with her public key instead of Bob's public key, and Alice will send a message encrypted with Trudy's public key. Then Trudy can decrypt the message, read the contents, and maybe change it, and send the message, forward the message to Bob. Bob will also receive the message from Trudy, decrypted with his private key, and read the contents that might be altered. Trudy can also send Bob her public key, and make him assume that it's Alice's public key, and the same would happen to Bob. So Trudy will be in the middle of Alice and Bob, giving them both her public key, and she can read and alter their messages. This is what we know as man in the middle attack, or in this case, woman in the middle attack. That's why we need confirmation that Bob's key is actually Bob's key, not Trudy's key. Here came the certification authority role. A certification authority is an organization to certify public keys. Suppose that Bob wants to allow Alice and other people to communicate with him securely. He goes to the certification authority with his public key and his passport or driver license, his ID, and asks to be certified. The certification authority will issue a certificate and sign it, stating that this is Bob's public key. He will get a floppy disk, he will get a memory stick, whatever the form of the portable memory is, and he will pay fees to the certification authority in exchange of certifying him. Public key management standard is called X509. X509 is a standard of managing certificates. It describes the certificate fields, and it has abstract syntax notion used to encode the certificates. The fields are of X05 certificates are version, where the version of X509 is written. The serial number, this is uniquely identifies the certificate along with the CA name. Signature algorithm is the algorithm used to sign the certificate. issuer, the CNA, validity period, starting and ending date for the validity of the certificate, subject name, the entity whose the key belongs to, Bob, for example, and the public key for the subject who has applied to the certificate. Issuer ID, it's an optional field that has ID uniquely identifying the certificate authority. Subject ID is another optional field with ID uniquely identify the certificate holder. And we have multiple extensions to the header. Then the signature, which the certificate authority will sign it using hash function. Certification authorities are very important. The question was, how can we handle them? Do we have a central certification authority for the whole internet? That won't be very practical and it will be a choke point. Rather than this, they become public key infrastructure with a hierarchy where there are root certification authorities that certifies regional certification authorities, and this in turn certifies certification authorities in the region. So the root has a certificate to say that this is a certified regional authority, and the regional authority will have a certificate to say that this is a certified certification authority, and the certification authority will give the individuals and organizations their certificates. Where certificates are stored, one option is to have each user to store their own certificates. Another option is to save it in the DNS server. And a third option is to use lightweight directory access protocol. What happened if a certificate was revoked because the individual has done something wrong or because he didn't pay his fees? There are what we call CRL, certificate revocation lists, that giving the serial numbers of all certificate that has been revoked. It's stored in the, as we have said, in the DNS or in the lightweight directory access using lightweight directory access protocol, and it's updated periodically. If we compare symmetric keys to asymmetric keys encryption, we will find that symmetric key encryption only requires single key, both for encryption and decryption. Asymmetric keys requires two keys, one public for encryption, one private for decryption. The size of ciphertext is the same or smaller from the original plain text in symmetric key algorithms. The size of ciphertext is the same or larger than the original text in the asymmetric key algorithms. The encryption process is very fast, while the encryption process is very slow in public key algorithms. In symmetric key algorithms, it uses large amount of data. It's used when large amount of data need to be transferred. The asymmetric key algorithms are used when small amounts of data are to be transferred. The symmetric key algorithms provides confidentiality. Asymmetric key algorithms provide confidentiality, authenticity, and repudiation. The length of the key used is 128 to 256. The length of the keys in asymmetric key algorithms are 2048 and higher. That provides more security. Symmetric key encryption utilizes low resources compared with asymmetric key encryption, and it's used efficiently to encrypt large amounts of data. Comparatively, it's less efficient when handling large amounts of data. Security is lower because only one key is used for encryption and decryption. Security is higher because there are two keys, one for encryption and one for decryption. See you in the next part.